Right. Okay, thank you for the introduction. So this is joint work with Konstantin Chow and Suha from Paris. So this talk is in the context of stateful distributed systems. And so, whoa. If you're trying to build a distributed stateful application, there are at least a few things that you want to have. So you want your application to be scalable. That means that as your workload increases, you get more clients. You want to be able to allocate more resources to put more nodes to serve your system. You want your application to be available most of the time. So that means that whenever you get a client request, you want to be able to answer as quick as you can. And these two goals you can achieve by having your state of your application replicated across the nodes of your distributed system. From the developer point of view, you also want to have programmability. You want to have the system be easy to program. So within the context of stateful distributed applications, this kind of means strong consistency. Strong consistency means that whenever a node performs an operation, updates the state, all other nodes will get to see that update almost immediately and at least in the same order. Now, unfortunately, this is impossible to have. You cannot have both availability and consistency in a distributed system that tolerates network failures. This is known as the Cap Theorem by Gilbert and Lynch. And this is bad news. This means that either you get availability and you respond quick, or you get programmability and programming is easy. But now, how do we pick, right? I mean, this is a really hard problem. It's an unfortunate situation. So people have thought about this for quite a while, and CRDTs, conflict-free replicated data types, are a reasonable compromise between these two goals. So what CRDTs give us is availability. So it's a replicated data type, so the state is copied among all the nodes of the system. And because the state is copied in all the nodes, it's network partition tolerant. So what that means is that whenever a client makes a request to a node in the system, that node will immediately answer to the client without having to synchronize with every other node. That also means that because we're not synchronizing on every client request, we might have nodes that diverge in their state for a while. So we don't have strong consistency, but we have something that is, relatively okay. This is called strong eventual consistency. What this means is that given a certain amount of time, if we allow all the updates that have been done to propagate to all the clients, then we will end up in the same state, okay? So this is built around the notion of abstract data types, so data types like lists, trees, registers. And the mechanism by which CRDTs achieve this goal is by having a conflict resolution algorithm that it's able to detect when there are concurrent updates and deterministically choose the state that we're all going to go to. All right, so let me illustrate this with an example, and this is going to be the running example for the rest of the talk. This is called a replicated global array, RGA from now on, and it's supposed to represent a list or something like a list. So at the top left, you have the data type abstraction. So initially, our list contains only one element, a start element, and we have three operations: add after AB, which adds the item B after the item A, remove A, and read. So let's run this. Suppose we have three replicas with the initial state list with only the start, and somebody connects in Latin America, and it reads the state, and it adds A after the last item that we saw. So we're going to update the state, and we get start A. And so eventually, this update is going to be propagated to all the other replicas. We're, again, in the same state everywhere. Somebody connects from China, does the same thing, reads the state, adds B after the last item. We get AB. This is propagated. Everything is fine. Now, obviously, the question is, what happens if we get two concurrent add-after operations, right? And so if they're really concurrent, we're going to end up with states that are start A in Latin America and start B in China. So the question is now, how do we reconcile this, right? I mean, who goes first, A or B? So before I go into how to implement this, I'm going to have just a tiny disclaimer. And this is to say that a CRDT based on a certain type X, say a list or a register, is not actually a list nor a register, okay? It's a CRDT, it has weird behaviors. So I'm going to illustrate with a multi-value register CRDT, which is supposed to represent a register. So suppose we start with a register that has 0, and then two different replicas in parallel assign 1 and 2, all right? So if we now try to read, if we read from the first replica, we get 1, that's fine. If we read from the second replica, we get 2, that's also fine. But what happens when these states are merged? Well, it turns out that because neither of them is before the other, we're going to get a set. We're going to get 1, 2. This is a behavior that you would never get with a traditional register, right? So, and this has to be there in the spec, because this is something that could happen. So this means that this is not really a register. All right, so that's important. So let me go back to our RGA example. So this is the code taken from the paper, but it's very complicated. Well, not very complicated. It's a little bit complicated, so I'm just going to simplify it a lot. And I'm just going to leave add after and read. So the way this data type is organized is with actually a tree. So the tree is depicted in the gray box. And so the parent-to-child relationship in the tree is an under approximation of the add after relation. I mean add after as in the method add after, not in the list. On top of that, each item is each box in the tree is going to have both the item that was inserted and a timestamp. And so this timestamp is sampled when the item is added into the tree, and it's greater than any other timestamp that we saw in the replica that added the item. So for instance here, the timestamp TA of the item A has to be greater than 0. The timestamp TC has to be greater than TA and T0, and so on and so forth. Now, because replicas can be executing this disconnected from each other, these timestamps could end up being equal. So in the case that they're equal, we're going to use the replica identifier to disambiguate. So that builds a total order in this relationship. All right, and so reading uses either the parent-to-child relationship, and if that's ambiguous, so if you have two concurrent things, we're going to use the timestamp to order the thing. So for instance here, because the timestamp of C is lower than the timestamp of B, B was added after, so therefore it goes before B in the list. All right? All right, so this is an execution that could have ended up in this state. So we started by adding A after the star, and then in parallel we added B after A and C after A. All right, so let's execute a little bit this algorithm. So let's say that now from this state, we add E after C. So what that's going to do is just going to add a node following from C with a timestamp that is greater than any other timestamp that we had so far. We do the same thing on the other branch. We add D after C, same thing. We add D as a child of C with a timestamp that is greater than any other timestamp. And now to reconcile the two states that have been diverted, we're just going to overlap the trees. And because we know that the timestamps are totally ordered, we get some resolution. In particular here, I chose to have TE be lower than TD, so we get A, B, C, D, E. Okay? So from now on, I'm going to call the thing at the bottom, which is the execution, an execution. It's the execution of the implementation. And the thing at the top, I'm going to call it a history. A history captures the causality in the execution. All right, so then we're trying to specify data types. So a question is, can we actually argue that this is a legal execution for RGA? And so let's try to do this. Is there any way to look at this as if it were a list? So let's try to do that. So we start with the list with only the star. We add A after the star, we add C after A, and this is important, and then we add B after A. The reason why we have to do it in this order is because if we did it in the opposite order, what we will get is A, C, and B, right? Because we're adding after A. Okay, and doing this, we can continue, and we get the list that we wanted. So everything looks fine. This looks like a list. This is a good trace. Unfortunately, so assuming that this is what we're only going to see ever, we could say, okay, so the specification of this thing is really simple. We have a list on the left. If you do add after AB, you just add B after A, and that's it. And then the read just returns whatever list you had at the beginning. So the return value of read is after the double arrow. So unfortunately, this doesn't always work. So let's just now modify the example a little bit, and let's do a read after each add after operation. Because on the top replica, C is not seen, we get star AB, and the bottom replica, we get star AC. So let's try to explain this. We can start just as we did before. Let's take the bottom branch. We add C, then we read, we get AC. Then we can add B, but then when we try to read, we can't just ignore that a C was added before. So we can't end up with star AB. And so this is a problem. And the problem stems from the fact that the replica that did the read that ended up in star AB did not see the effects of the add after AB because they were, concurrent. They were disconnected at that point. So that's one thing that we have to cope with. And the way we're going to cope with this is by, in our linear history, allowing some operations to ignore some operations in the prefix. So for instance, here, we could just say, okay, for the last read, let's pretend that these two things didn't happen. So we still have a linear history, but we're allowed to ignore some things that had not been propagated at that place yet. All right, so now this is good. And this is the first observation. So visibility, the fact that visibility is not total requires us to tolerate some missing updates. Okay, good. So what about remove? I've been ignoring remove for up to now. So let's assume that we have a concurrent add after AB and a remove of A. Well, if we try to linearize add after AB after add after AB after A has been removed, we're in a problem, right? Because you can't add after something that is not there. So RGA, instead of actually removing the object, is just going to mark it as being removed. So reads don't return it, but the item stays there. That makes the placement of B unambiguous, all right? So this is usually called a tombstone as an implementation detail, and that's what we're going to be doing. All right, so if we try to explain this, obviously we have to add A after B before we remove A, because otherwise the precondition of add is not met. So this is the trace that we get at the end. So this is a good trace. Obviously, again, this is not always going to work. So what happens if we have two branches? In one branch we remove A and then we add after B, and then in the other branch we remove B and then add after A. Well, we could also again try to explain this, but the same thing that happened with the reads is going to happen again. We're going to end up in a place where we want to add B after C, but B has already been removed. So it turns out that this is not as easy to fix as just ignoring one operation. I'm not going to go into the details of why that is. The trace is really long. But what this means is that, so first of all, first observation is add after AB has as precondition that A is in the list, and we need to preserve this in our specs. And the second observation is that the conflict resolution algorithm cannot always be ignored from the specification. So now we're going to have to taint our specifications a little bit to say, well, actually something weird is happening when there are concurrent updates. So this brings me to the actual specification we have for RGA. So now our state, our abstract state, is a list and the tombstone. So this is a set of things that have been removed. And the spec of add is just add the item wherever it needs to be. So add after AB puts B after A. Remove A doesn't change the list at all. It just added to the set. And read just returns the list minus the items that have been removed in the tombstone. So there are two things to observe here. So the first one is that the specification needs to talk a little bit about the conflict resolution. All right, so we can't avoid this. If you think about the multi-value register, if we don't talk about the fact that there could be concurrency and we could have weird behaviors in the spec, then you would never expect to see a set. But importantly, the specification does not need to talk about all the details of the conflict resolution. And in particular, the details, the way that the specification specifies conflict needs not to be related with the way the implementation implements the conflict resolution algorithm. So this is important. So given these three observations, I'm going to give you a pictorial view of our definition of replication-aware linearizability. So what replication-aware linearizability requires is that for any history of an actual execution of the implementation, there should be a relatively equivalent linear history of the specification. So this is actually a linear trace, such that for each item, so for instance the pink one, we can explain the behavior of that item modulo removing some elements in the prefix. So for instance, for the pink one, we can get rid of the red one. For the yellow one, we can get rid of the green one. All right. So far, so good. So this brings me to my second disclaimer. Replication-aware linearizability is not linearizability, okay? So like, so this is not the standard Harley-Wien definition of linearizability. In particular, we don't care about the real-time or wall clock order that is important for the definition of linearizability. However, we want to call this linearizability as opposed to sequential consistency or serializability or whatever else you want to, because it shares some nice compositional properties with linearizability. So that's why we picked the name linearizability. All right, on top of the specs, we provide a proof methodology to show that a certain implementation of a CRDT meets the specification, replication-aware linearizable specification. So this is a typical refinement argument. So this is building a simulation. And it can be decomposed in two parts. So firstly, a commutativity argument that says whenever you have two operations happening in two different replicas at the same time, the order in which you put these operations in the linear history doesn't matter all that much. And then the other part is a typical refinement mapping. You have to map the states in the implementation with the states, the abstract states of your specification. Moreover, we observed that most of the CRDTs that we looked at fall into two categories for doing these proofs. So the first one is your typical linearizability with linearization points strategy. This is called for us the execution order linearization. You just put the operation at the linear time where it happened. And this works remarkably well. This was a surprise to us. This doesn't work always, though. And so in particular for the RGA example that we were looking at before, you have to look at the timestamps. So the second type of proofs that we're going to build is based on the order of timestamps. So for instance here, because the timestamp of the green update is smaller than the timestamp of the red update, we have to order them in that way in the linearization. Okay, so with that, we proved a number of, well, most of the CRDTs that we found in that survey paper that I showed earlier. And we were able to give relatively simple specifications and prove that they were correct. I didn't talk much about this, but CRDTs come in two flavors: operation-based, where what we send to the other replica is a summary of the operation, or state-based, where we send is just our current state. There are differences between them. It doesn't really matter for this talk, but this is depicted in the middle column. Our proofs are formalized in the Boogie program verifier using a trick to show commutativity. And you can find them in this link at the bottom. So with that, I'm going to finish my talk. So in summary, we're able to provide really simple specifications for CRDTs, so things that an actual programmer can look at and say, okay, so yeah, I understand what this does, and I now can write my program. We provide proof methodologies tailored to the different types of conflict resolution that we see. I didn't talk about this because I didn't have time, but our properties have really nice, our definition has really nice compositionality properties. And it applies to many known implementations out there, as I've summarized in the table. So yeah, so that's the end of my talk. Thank you.
Hi, Lars Kroll from KTH in Sweden. Thank you for the nice talk. It was very interesting. I was wondering, there is a slightly stronger notion than sequential consistency, that's somewhere between sequential consistency and linearizability, which is essentially sequential consistency that respects logical time order, that just respect happens before order.
Right.
Could you comment on what you think the difference between your abstraction and this model is? Because they seem very similar to.
So you're saying, are you talking about strict serializability? Is that what you're referring to? I mean, I'm not sure what this thing is.
You can essentially, so you can build an algorithm that uses for example, for atomic register, right? If you think of atomic register algorithm, you can build a variant of this that respects timestamps like you do, but logical timestamps, like Lamport timestamps. And if you do this, you get something that is slightly stronger than sequential consistency, and it has exactly these nice compositionality properties.
If it's stronger than sequential consistency, it's definitely going to be stronger than this, right? Because like we're allowed to ignore some things that happen before you end the trace. So I don't think, if it's stronger than sequential consistency, I think it's definitely going to be stronger or incomparable to ours.
Probably incomparable.
Yeah.
Okay.
Most likely
Thank
incomparable.
You.
Yeah, no problem.
Hi. There are a bunch of other distributed consistency models, of course. Could you quickly characterize something that, would be allowed under, say, causal plus consistency, but definitely disallowed under RA linearizability?
not sure I can come up with an example off the top of my head. If you have something in mind.
No, that's fine. I'm just wondering, any best way to say
so
what the strengths of RA linearizability
RA linearizability looks a little bit stronger than causal plus. I mean, we at least have causality, so I think we're probably going to be stronger or incomparable, but I cannot come up with an example off the top of my head.
Okay, I'll talk about
Yeah, thank you.
Let's thank our speaker again.
Thank you.